Advanced Higher Chemists, let's go over this question from the 2014 Advanced Higher Chemistry SQA past paper. We're given information on how a buffer solution has been made, and we're first of all asked to calculate the concentration of potassium ions and hydrogen ions. One thing to bear in mind is that now you wouldn't see hydrogen ions written there, you would see hydronium ions, the H3O positive ions, written instead. But this is something you want to bear in mind for your section 2 answers. Make sure you write hydronium ions and not hydrogen ions. But back to the question, for calculating the potassium ion concentration, this is pretty straightforward because those are in the potassium hydroxide, which is a strong base, so it will fully dissociate and completely ionise. So all we need to do to work out the concentration of potassium ions is a simple NCV calculation. So to start off by working out the moles of potassium hydroxide that were added, we just use the concentration times the volume, which would be 1 mole per litre times the 20 centimetres cubed put into litres. That then means that there was 0.02 moles of potassium hydroxide. Because potassium hydroxide has got a 1-to-1 ion ratio, that means that if there's 0.02 moles of the compound, there will be the same number of moles of the potassium ions. So now we've got the number of moles of the potassium hydroxide, we just need to work out the volume of the solution. Now you might be thinking, well, the volume is 20 centimetres cubed, but that's the volume of the potassium hydroxide solution. We're now concerned with the buffer solution, so we need the volume of the solution that was made. If we add up the volumes of the two solutions that were added together to make the buffer solution, we'll be able to work out that the buffer solution is actually 60 centimetres cubed. Dividing that by 1,000 to turn it into litres gives you 0.06. Now we just do C equals N over V, which gives you 0.33 moles per litre. And that's your final answer for that one. Now the hydrogen ion or hydronium ion concentration is more difficult because the ethanoic acid is a weak acid, so it will only partially dissociate. So in order to work out the concentration of hydronium ions, we're actually going to have to work out the pH of the buffer solution and then use that pH to work out what the hydronium ion concentration is. So we basically need to use our pH of a buffer equation followed by a rearrangement of the pH equation. So if we start off with our pH of a buffer calculation, the pK is that of ethanoic acid, so you will find that in the data booklet. That is 4.76 minus log 10 of the concentration of our acid divided by the concentration of our salt. So to work out the concentration of our acid, we do something very similar to what we did with the potassium hydroxide. We do the concentration times the volume. Doing that then gives us 0.04 moles. When you're using this equation, you can actually have number of moles in here. As long as they're both number of moles, it's okay. Or they both have to be in moles per litre. But to make our lives a bit easier, we'll just keep this in moles. So the moles of the acid is 0.04. Now we just need to work out how many moles of salt we made. Jotted down the balanced equation here. So remember, we had 0.02 moles of the potassium hydroxide and 0.04 moles of the ethanoic acid. Doing a wee limiting and excess comparison, which is quite easy here because it's a 1-to-1 ratio, that means this is your limiting reagent, which means you're only going to produce 0.02 moles of the salt. So then we can put our 0.02 moles here, and that gives us a pH of 4.459. Now we just need to rearrange this equation to be able to use the pH to work out the hydronium ion concentration. This one isn't given to you in the data booklet, so it's probably a rearranged equation that's worth remembering, but the hydronium ion concentration is equal to 10 to the power of the minus pH. So if we put our pH that we've just calculated into here, that'd be 10 to the power of minus 4.459. This then gives you the final answer of 3.46 times 10 to the minus 5 moles per litre, or you could round it to 3.5 times 10 to the minus 5 moles per litre. Hope that helps, but what I will say is this is from an old advanced higher chemistry paper where the calculations are sometimes a little bit trickier, so you probably wouldn't have to do that much in a calculation for buffers now. So have a look at the newer papers and you should be able to find buffer calculations there that are a little bit more straightforward.